It is a great pleasure to introduce Jason Alicea. Jason, thank you so much for accepting the invitation. It is a great pleasure to have you here. And let me give you a brief summary of Jason's background. So Jason got his PhD in 2007 from the University of California in Santa Barbara. Afterwards, he was an assistant professor of physics at UC Irvine. Then afterwards, he was associate professor in Caltech in 2012. And starting in 2015, he is professor of physics at Caltech. And apart from that, he is also one of the members of Caltech's Institute of Quantum Information and Matter. From the physics point of view, Jason is especially interested in exotic phenomena that emerge from the interplay between topology and quantum mechanics, and in particular, he's interested in exotic physics that can be potentially useful for topological quantum computing, and in particular, the emergence of anyons in condensed matter systems. From the more, let's say, physics, he is especially interested in designing experimental realistic blueprints to observe and design anyons. And in particular, he's interested in designing protocols for detecting and manipulating anyons in specific solid-state architectures. Overall, he's interested in out-engineering nature, both from the point of view of using these exotic excitations for purposes related with quantum information, and also to reveal new effects of quantum mechanics that so far we have not been capable of observing in a lab. And today, Jason is going to tell us about a spin on topological quantum computation. And with this, Jason, thank you so much for accepting the invitation. We look forward to your talk, and the floor is yours.
All right. Well, thank you so much for the very kind introduction. Actually, you captured my taste in physics perfectly in what you just described. So my talk today is motivated by a possible gift from nature in the form of certain magnetic insulators that could realize exotic phases called quantum spin liquids. The particular kind of quantum spin liquid I'll be focusing on today has potential applications for intrinsically error-resistant topological quantum computing hardware. As I'll describe, though, fully unwrapping that gift from nature and harnessing all the interesting features of these quantum spin liquid phases poses some very subtle challenges. And as my talk goes, I'll provide some ideas for how we can begin to overcome those subtle challenges and work our way up towards applications with these quantum spin liquid systems. Oh, and maybe I just at this point add that I very much would welcome questions during the talk. So please don't be shy if anything comes to your mind. If anything I say is confusing, just ask. All right, before I go any further, I wanted to pause to just acknowledge my collaborators. I've been working on this subject now for probably 3 years or so with a bunch of my friends here. Sorry, there's something that popped up. I'm just going to hide this. Sorry. Okay. So I wanted to in particular just call out the junior people that I've had the pleasure of working with on these issues. So first, my current grad student, Yue Liu, Kai Cloakey, who's a former Caltech undergraduate, who's now a first-year grad student at Berkeley, or actually maybe he's in his second year. Time has been very difficult to keep track of during the pandemic. Dave Asen, who is my former PhD student, now is a postdoc at Station Q. And finally, Kevin Slagle, who's a postdoc fellow at Caltech. All right, so to set the stage, I'm going to begin by introducing to you I think, very interesting phenomena of non-Abelian anyons and how they can be useful for so-called topological quantum computation. Non-Abelian anyons are emergent particles that can be born within certain kinds of topological phases of matter. So for the purpose of introduction, let's imagine that you have at your fingertips some topological phase of matter that hosts these emergent particles. So let me sketch to you the interesting characteristics that make them so special. So one of the interesting features of non-Abelian anyons is that as you start populating them into your host system, that system acquires an exponentially growing ground state degeneracy. For example, suppose that when you introduce 2 non-Abelian anyons into your system, the system finds itself with not 1, but 2 degenerate ground states. Introducing a second pair would grow that ground state degeneracy to 4. A third pair gives you 8 states and so on. So you get this exponentially exploding set of degenerate states available to your host platform. That property hopefully sounds kind of peculiar, But I want to stress that by itself, ground state degeneracy is really not that extraordinary. In fact, at this point, you might counter and say, well, what about a system of free spin-a-halves sitting within some insulating material? And by free spin-a-halves, I just mean a spin degree of freedom that energetically doesn't care whether it points up or down. Indeed, every time you introduce an extra free spin-a-half to that insulating system, you would grow the ground state degeneracy by a factor of 2, giving rise to exactly the same kind of counting that I just showed you for the non-abelian anyon problem. So that's true, but I want to stress that there's a fundamental difference between the kind of ground state degeneracies one gets for these free spin-a-halves and the kind of ground state degeneracy that non-abelian anyons give us. For one, it's at least in principle possible to perform local measurements of these free spin-a-halves. For instance, you could imagine going in and measuring the magnetization associated with each one of those spins to reconstruct exactly where your system lives within that space of degenerate ground states. In the case of non-abelian anyons, that's fundamentally impossible. There are no local measurements you can perform that give you any information about which of those ground states your system is actually populating. A second and closely related feature is that the ground state degeneracy for these free spin-a-halves is by no means robust. You could easily imagine partially or fully lifting that ground state degeneracy by applying magnetic fields which favor, let's say, spin up over spin down. Okay, and that would certainly split that ground state degeneracy. In sharp contrast, once again, the ground state degeneracy we find for non-abelian anyons is resilient to arbitrary local perturbations, whether they're magnetic fields, electric fields, disorder, and so on, as long as those perturbations that you apply are not sufficiently severe to destroy the topological phase that allows these non-abelian anyons to be born in the first place. All right, so what we learned from this comparison is that these non-abelian anyons carry unusual zero energy degrees of freedom that span a very special kind of ground state degeneracy consisting of states that are crucially all locally indistinguishable from one another. All right, so this is the first key characteristic of non-abelian anyons. They generate a very special kind of ground state degeneracy consisting of states that you cannot distinguish via local measurements. All right, so let's go a little bit further now. Suppose that by some means you initialize your system into one of those degenerate ground states, which I'm going to call psi sub I. And here I is just a label which tells me which of these states I choose to initialize into. All right, so following that initialization, we can take two of these non-abelian anyons and then slowly exchange their positions, slowly move them around each other until they swap positions. Now, although these are identical quantum particles, just like ordinary electrons and fermions and bosons, this swap has a very non-trivial effect on the system. So in particular, that exchange that we just performed of those identical quantum particles fundamentally transforms your system's quantum state. More precisely, that exchange will rotate your system from one of these locally indistinguishable ground states to, in general, a different locally indistinguishable ground state. Okay, so that rotation is quantified by a so-called braid matrix Uij. And that kind of exchange statistics is called non-abelian exchange statistics. And we call this non-abelian because the order matters. If you perform multiple exchanges, the final state that you end up in is very sensitive to the sequence in which individual exchanges are carried out, essentially because matrix multiplication is in general non-commutative. All right, so this is quite interesting. This is actually the most exotic kind of exchange statistics that nature allows us to find even as a matter of principle. All right, so this is the second key characteristic of non-abelian anyons. The third is that they exhibit so-called non-trivial fusion rules. So what this means is that if you take a pair of non-abelian anyons and then bring them together in space, they can always combine to form at least two different kinds of particles. So this may seem a little bit mysterious. So to put this in context, you might imagine a situation of taking an electron and positron and bringing them together. So electron and positron, those are antiparticles of one another. There's no question when you bring them together, they will just annihilate each other. But for non-abelian anyons, there's never a unique answer. Bringing a pair together might cause them to annihilate, or that pair might combine to form some completely different kind of non-trivial particle. Right, so that's the third key feature. They exhibit non-trivial fusion rules. So these three features, if you want to think about, you could think about these as defining the essence of non-abelian anyon DNA. This is what makes these emergent particles so special. And I think from a basic science viewpoint, this is really just phenomenally interesting, a bit of quantum science. And this fundamental aspect alone makes these things well worth pursuing in the lab. Interestingly, however, there's also a potential technological application of this physics, as Alexei Kitaev taught us a number of years ago. So in particular, Alexei taught us that if you had a system of non-abelian anyons, you could in principle exploit these remarkable three features to build so-called topological quantum computing hardware that was intrinsically immune against errors. So let me sketch the basic idea of how a topological quantum computer would operate. So first of all, these locally indistinguishable ground states are a very attractive place to encode quantum information. Essentially the same property that makes it difficult for the observer to distinguish between these states via local measurements also endows qubits encoded in that subspace with intrinsic resilience against local environmental noise. So by using these non-abelian anyons, we automatically have a very secure place to encode quantum information. But now by virtue of non-abelian statistics, we also have access to a set of intrinsically fault-tolerant quantum gates that we can act on those qubits. So from this point of view, you can view these braid matrices Uij, which again, we're encoding exactly how the exchange rotated your quantum state in this low energy Hilbert space. You can think about those braid matrices as encoding quantum gates that process your qubits in ways that the user controls, depending on which pairs you swapped and in what order. So ideally, this is how one would actually run quantum algorithms. You would perform a quantum computation by choosing some judicious set of exchange operations to apply whatever set of quantum gates that you were interested in imposing. And finally, to perform readout at the end of a quantum computation, we can exploit non-trivial fusion rules to that end. So here the idea is that by bringing these particles together, you convert these locally indistinguishable states into locally distinguishable states that you can read out via conventional means by basically detecting exactly how these particles fused. Okay, so this is how you can perform readout at the end of a quantum computation. All right, so in a nutshell, this is how non-abelian anyons can be useful for topological quantum computation. I like to describe this as Alexei's $3 million idea, because in fact, he won $3 million for this proposing this physics as one of the inaugural winners of the Fundamental Physics Prize some years back. Now, you might say that Alexei already answered the $3 million question in this field, but the $1 billion question remains outstanding, namely, how do you build the hardware to bring this elegant idea to experimental life? Roughly speaking, there's two strategies in which one currently tries to address that $1 billion question. The first broad strategy seeks to engineer designer realizations of topological superconductors that harbor so-called Majorana zero modes. Majorana zero modes are the simplest kind of zero energy degree of freedom, exotic zero energy degree of freedom that underlies all the interesting non-abelian anyon physics that I described on the previous slide. All right, so here the idea is that you, rather than trying to get lucky, you try to essentially force electrons into realizing interesting topological phases with non-abelian anyon physics by judiciously combining ingredients that individually are well understood. And as Jose said in his introduction, the idea here is to try to out-engineer nature in some sense. But nature is not easily out-engineered, as we all know. Nature also supplies us with intrinsic realizations of non-abelian anyons, these potential realizations, where here the idea is quite a bit different. In this intrinsic approach, you rely on some non-trivial interacting Hamiltonian to stabilize some exotic topological phase that supports non-abelian anyons. In fact, the first ever potential non-abelian host platform fell into the second category and corresponded to certain kinds of fractional quantum Hall states. A more recent entry into this list of potential intrinsic realizations involves something called quantum spin liquids. Now, although I've spent much of the last decade of my research in the top half of this slide pursuing designer realizations of topological superconductors and Majorana zero modes, for the purpose of this talk, I'm going to focus actually on this bottom right and think about quantum spin liquids as potential non-abelian anyon hosts and potential topological quantum computing platforms. All right, so for the rest of the talk, I'll be focusing in this particular possible intrinsic route. All right, so a natural question at this point is what is a quantum spin liquid and under what circumstances can they host non-abelian anyons? So quantum spin liquids were invented by the late great physicist Phil Anderson back in 1972. And in the intervening decades, the community has come to understand quantum spin liquids as exotic ground states for spin systems that evade magnetic ordering and other kinds of symmetry breaking ordering all the way down to zero temperature due to strong quantum fluctuations, leaving behind very interesting characteristics, including the emergence of fractionalized excitation. Now, in a really breakthrough 2006 paper from Alexei Kitaev, he wrote down an exactly solvable model for a quantum spin liquid that provides a very attractive way of understanding exactly what a quantum spin liquid is and all the interesting features that they exhibit. So Alexei's model involves a spin and a half degrees of freedom arranged on a honeycomb lattice governed by the Hamiltonian shown here. All right, so I've colored the bonds on this honeycomb lattice blue, green, and red. Along all of the horizontal blue bonds of this lattice, it's the x components of spins that couple to one another. Along these diagonal red bonds, it's the y components that couple. And along all the diagonal green bonds, it's the z components that couple. Now, these blue, red, and green terms are trying to polarize the spins along incompatible directions. So the blue bonds would like the spins to point along plus or minus x. Red bonds would like the spins to point along plus or minus y. And similarly for the green bonds. So clearly, you can't maximally satisfy all of these three kinds of terms at the same time. This corresponds to the always interesting phenomenon of frustration. So frustration is always interesting because it tends to suppress the tendency for conventional physics like symmetry breaking order and can promote more interesting effects like quantum fluctuations, potentially leading to more exotic ground states, including in this context, quantum spin liquids. So this model is in fact exactly solvable. And that exact solution reveals that these spins indeed realize a quantum spin liquid as their ground state. Let me just say one sentence about how one actually solves this model exactly. So there's a very handy trick for doing this. One can take these spin and a half degrees of freedom that this Hamiltonian is built up from, and decompose those spin and a half degrees of freedom in terms of a quartet of so-called Majorana fermion operators. This is a trick that you can always do. It's just some legitimate way of representing the Hilbert space for a spin and a half degree of freedom. The magic in this context, though, is that when you rewrite this Hamiltonian in this Majorana fermion language, there's some miracle that takes place, and the Hamiltonian effectively reduces to a problem of free Majorana fermions coupled to their nearest neighbors on the honeycomb lattice. Now, when you think of free fermions on a honeycomb lattice, that might evoke a different but related problem, namely graphene, where you have electrons hopping between nearest neighbor sites on a honeycomb lattice. So with that connection in mind, it may not surprise you to learn that the spin liquid phase hosts gapless excitations in the form of a massless Dirac cone. So it's very similar in that sense to graphene, which also famously harbors massless Dirac fermions. I want to emphasize, though, that despite that a common aspect of having Dirac fermions here and in graphene, there's a fundamental difference which I should very prominently emphasize. So first of all, in the context of graphene, those Dirac fermions are built out of ordinary electronic degrees of freedom. And in principle, you could take one of those Dirac electrons and then take it out of your graphene sheet and, for instance, drag it to a lead. In this context, this is much more exotic. These Dirac fermions are much more exotic because we started from a purely bosonic spin system. And from the interactions among those purely bosonic spins have emerged a new kind of degree of freedom, namely these emergent fermion degrees of freedom. Okay, so these are emergent degrees of freedom that have been born within a purely bosonic spin system. This means that even as a matter of principle, you cannot take one of those emergent Dirac fermions in this quantum spin liquid context and peel it out of your spin system. That's impossible to do. Those fermions only have integrity in the spin system that allowed them to emerge in the first place. All right, so this at this level, this is already quite exotic physics. So this exactly solvable Hamiltonian reveals the presence of a spin liquid ground state hosting a gapless emergent fermionic degrees of freedom. Now the situation gets even more interesting, it turns out, if you apply magnetic fields and break time Versal symmetry. Right, so that magnetic field leads to this innocuous looking Zeeman term. That innocuous looking Zeeman term actually does something rather extraordinary to the spin liquid phase. Right, so in particular, that the breaking of time Versal symmetry by that magnetic field will open a gap in this Dirac spectrum, taking your gapless spin liquid phase into a fully gapped spin liquid state that harbors, quite amazingly, non-abelian anyons. All right, so let me now sketch the basic universal features of this gapped non-abelian spin liquid phase. Okay, so first of all, that spin liquid is gapped in the interior, but it does host a gapless edge state in the form of a chiral Majorana fermion. All right, so if you're not familiar with this jargon I'm using of chiral Majorana fermion, you can just think about that chiral edge state as a one-way street for heat. So in other words, if you deposit some energy along the boundary, that energy will just propagate unidirectionally in some particular orientation. All right, so that's the interesting edge physics that these non-abelian spin liquids carry. In terms of gapped bulk excitations, there are two non-trivial types. So first, there are gapped non-abelian anyons, which I'm going to denote by sigmas in this talk. And second, there are gapped emergent fermions, which I'll denote by psi. All right, so as the name suggests, these sigma particles exhibit non-abelian statistics when you swap identical pairs. You in general get a rotation within your ground state subspace. These emergent fermions, as the name also suggests, they're fermions. When you swap them, your wave function gets a statistical minus sign, just like for conventional fermions like electrons. When you take an emergent fermion all the way around a non-abelian enyon or vice versa, there's also a non-trivial statistical phase of -1 that's acquired. In terms of fusion rules for these non-abelian anyons, if you bring two of these non-abelian anyons together, they can annihilate each other, or they can combine to give you one of these emergent fermions. Now, if you view that fusion process in reverse, that tells us that you can pull a pair of non-abelian anyons out of the vacuum, or you can take one of these emergent fermions and further splinter them into a pair of non-abelian anyons. Okay, so those are all the universal features that we'll need to understand later parts of my talk. All right, so at this level, this discussion probably sounds very pie in the sky. You might look at this Hamiltonian and view it as very artificial because we've written down these maybe very strange looking bond-dependent spin interactions. And in fact, I know for sure that Alicea did not write down this Hamiltonian motivated by any particular compound, but rather he constructed this model solely for the sake of exact solvability. In a 2009 breakthrough paper by Jakellian and Kalulin, this problem was brought from pie in the sky theory into the realm squarely of experimental relevance. So in particular, Jakellian and Kalulin observed that there's a class of strongly spin orbit coupled magnetic insulators that actually rather naturally realize these bond-dependent spin interactions from Kitaev's honeycomb model as the dominant terms in the Hamiltonian. Of course, in any real material, there will always be additional interactions, which I'm not writing here explicitly, but just noting by these ... But at least there's some family of materials that we believe have dominant interactions of this Kitaev honeycomb type. So this key breakthrough paper led to what is now a very active experimental discipline pursuing a class of materials called Kitaev materials that fall that are believed to be described by Hamiltonians of this type. In this talk, I'm going to focus on one particular member of this Kitaev material family, namely alpha ruthenium chloride. So here's a possible phase diagram of alpha ruthenium chloride as a function of temperature on the vertical axis and magnetic field along the horizontal axis. So let's start by thinking about the zero magnetic field axis, which corresponds to this line here. At high temperatures, as is true for any material, the spins just thermally disorder and you just get a conventional paramagnet. When you cool the system down below about 7 Kelvin in this case, eventually magnetic order sets in. And this tells us that although these dots may be nominally small, they have a sufficiently severe effect on the system's ground state properties to destroy the gapless spin liquid phase from the Kitaev honeycomb model in favor of more conventional symmetry breaking order. Okay, so there's some magnetic order that appears at zero magnetic field. Now, the special feature of alpha ruthenium chloride is that by applying a magnetic field, so moving along a horizontal axis in this direction, you can actually kill that magnetic ordering. So here's the critical temperature line. You can actually watch the critical temperature for that magnetic ordering to come down all the way to zero, in which case you've destroyed that magnetically ordered state. And what you might hope appears on the other side is the non-abelian spin liquid phase from Kitaev's honeycomb model. Quite interestingly, there are a series of experiments that perform heat transport measurements that find some evidence that indeed a non-abelian spin liquid forms in this over at least some window of magnetic field. There's been some controversy about these results, though. I want to be very careful to not oversell the state of affairs here. Despite some tantalizing evidence, the situation here is far from settled. Some experiments see very clear signatures, what they interpret as clear signatures of non-abelian spin liquid phase. Other experiments see different phenomenology. If you're interested in a very recent synopsis of the status of this area, there's a very nice commentary that Patrick Lee wrote for the ConMat Journal Club that gives the state of the art on where this area stands. Okay, so I would like to view this as a tantalizing state of affairs, despite the fact that the situation is not settled. And for the purpose of the remainder of the talk, I'm going to be an optimist, and I'm going to assume that we can indeed find a non-abelian spin liquid, either in alpha ruthenium chloride or perhaps some other member of the Kitaev material family. Getting back to the question I posed in my title slide, when nature hands you, assuming nature hands us this gift of a non-abelian quantum spin liquid phase, the question is, what do we do with that gift? How do you begin to interrogate that quantum spin liquid phase to perform the kinds of manipulations and measurements that you would like to do to work your way up towards using that platform for fault-tolerant quantum information processing? All right, so in the next part of my talk, I'm going to give you a partial roadmap towards pursuing that end. All right, so there's a few minimal requirements that you would like to be able to achieve if you were going to take a quantum spin liquid and begin manipulating such a system to work your way up towards quantum information applications. So first of all, of course, we need to have a way of controllably creating anyons on demand, because if we can't do that, then you're kind of stuck at the ground level. You don't know how to create the very excitations that you need to create in order to define, for instance, a qubit subspace. You also would like to be able to manipulate those anyons once created to, for instance, perform braiding operations, these swaps that I mentioned earlier, and fusion operations, bringing those anyons together in space. And finally, we need to be able to detect individual anyons within that quantum spin liquid, both for readout purposes in an eventual quantum computing algorithm, but also more basically to just verify that you indeed have the kinds of anyons that you believe that you hope to have. All right, so these are the three minimal requirements that we'd like to achieve. Now, in other non-abelian enyon potential platforms, including topological superconductors and fractional quantum Hall systems, we actually have very well developed roadmaps nowadays for doing these three kind of basic elements. Now, those roadmaps are based largely on electrical manipulation of those electrically active superconducting and quantum Hall platforms. So here's just to give you a flavor. Here's a scalable nanowire-based architecture that features superconductors, semiconductors, quantum dots, gates, and so on. And here is an example of an electrically operated enyon interferometer that was proposed many years ago in the quantum Hall context for detecting non-abelian anyons and their exotic statistics. Now, despite the fact that those well-developed roadmaps exist, since they're based on electrical manipulation, those roadmaps cannot be naively imported to the realm of these Kitaev materials because those Kitaev materials are electrically inert by construction. Okay, so they don't respond to electrical currents, at least in a naive way. They resist electric fields and so on. So this presents what I think is a very interesting and subtle challenge. Essentially, if we're going to begin thinking about how to perform these elementary operations in quantum spin liquids, we need to basically revisit the roadmap from scratch, all the way up, all the way starting from first experiments up to more sophisticated qubit architectures and applications. All right, so I find this to be a very intriguing exercise, and been spending the last few years trying to figure out how we can actually, at least in experimentally plausible ways, begin to pursue these kinds of milestones. All right, so in what follows, I'm going to give you some ideas for how we can potentially perform all three of these operations in Kitaev materials, beginning with the on the right-hand side here with the question of single-anyon detection. All right, so I'm going to now describe to you a method of taking some of the anyon interferometry ideas born in the quantum Hall context and adapting them to these Kitaev materials. All right, so here's the interferometer that I'm going to use to try to detect individual anyons, excitations within the spin liquid. All right, so this shaded region here, that's my spin liquid. Over here, I'm going to introduce a constriction, and the role of that constriction will become clear shortly. And then this enclosed right region here, there's going to be some emergent particles, for instance, either a fermion or a non-abelian anyon that I would like to detect. Okay, so that's the goal, to figure out what's sitting in the right half of this device. So in order to detect what's sitting here, I'm going to use a pair of auxiliary spin degrees of freedom, one up here and one down here. This upper auxiliary spin degree of freedom is going to serve as an emitter of energy. This lower auxiliary spin is going to serve as a receiver of energy. So those two spins are going to funnel energy back and forth to one another via this intervening spin liquid phase. And the probability of shuttling energy from one to the other will turn out to depend on exactly what kind of particle is sitting in this in the right half of this interferometer. All right, so here's the basic idea of how this device works. Suppose that this emitter spin is initially in an excited state. Okay, so it would, if given the chance, it would like to relax and shed energy. And we can allow that spin to relax by coupling it to this one-way street for heat, to this chiral edge state sitting at the boundary of that spin liquid. Okay, so once those two subsystems couple, that auxiliary spin can flip, can shed energy into the spin liquid in the form of two co-propagating fermions moving to the right. Okay, so those two co-propagating fermions, they can just move along the boundary. They can just take the long way around, and eventually they can get picked up by this receiver spin, and that receiver spin can flip and absorb energy from that edge. Okay, so that's not the only way in which those two spins can exchange energy. There's a more interesting process that's enabled by the existence of this constriction. Okay, so let's think about this the same setup once again. So we start with this auxiliary emitter spin in an excited state. We allow that spin to shed energy into the edge. Now, when those two co-propagating emergent fermions hit this constriction, there's some probability that one of those emergent fermions splinters into two non-abelian anyons. Okay, one of those non-abelian anyons can take a shortcut and just tunnel across that constriction, and the other one can take the long way around and encircle whatever particle is sitting over here. Okay. Now, crucially, we have a non-abelian anyon encircling some kind of unknown quasi-particle with which it has non-trivial exchange statistics. Okay, so taking a non-abelian anyon around a fermion accrues a minus sign. Taking a non-abelian anyon around another non-abelian anyon leads to non-abelian statistics. And so there's information about what was enclosed, what kind of particle is sitting here by virtue of that exchange process. Okay, and once again, this receiver spin can absorb energy and flip its spin, even when that energy takes this more non-trivial path. All right, so those paths, along with other paths that I did not show you, can interfere with one another. And because there was statistical exchange information accrued during some of those paths, that interference depends very sensitively on the particle type that was enclosed in this interferometer. And that in turn tells you that the probability for this auxiliary receiver spin to flip depends on exactly what was sitting here. And therefore, by detecting that spin flip probability, you can infer exactly what kind of particle was sitting in the right half of your interferometer. All right, so this gives us a kind of time domain way of performing anyon interferometry, adapting the electrical interferometry schemes that were developed in the quantum Hall context. As a quick aside, there are other ways of performing interferometry in this context as well, including using heat transport measurements and counterintuitively electrical measurements if you're willing to pay some price in terms of material science tricks. But I really like this time domain anyon interferometry idea because I think it makes the kind of whittles the ingredients down to their bare essence. All right, so that's some idea for how we can detect individual anyons. Let me now go back to the left-hand side here and propose some ideas for controllably creating anyons on demand. All right, so what I'm now going to describe to you is a way of dynamically manipulating a quantum spin liquid so as to generate non-abelian anyons as finite energy yet long-lived metastable excitations. All right, so here's a device that potentially allows us to do that. All right, so this shaded region once again is the quantum spin liquid. As always, it'll have a chiral Majorana, this chiral edge state at its boundary, this one-way street for heat. I'm going to introduce now an additional pair of interior holes within which the system just realizes a trivial phase, for instance, magnetic order, one hole here and another hole here. Okay, so when we introduce those holes, we introduce a new boundary for that spin liquid, and correspondingly, there will be additional edge states, one here and another here. All right, so the key feature that I should stress here is that those holes, although they would rather not have any anyons at their boundary, they define energetically cheap locations for non-abelian anyons. Okay, more precisely, the energy cost for adding a non-abelian anyon to the edge states surrounding these holes scales inversely with the size of those holes. Okay, so the excitation energy, while finite, scales like 1 over the perimeter of those holes. And so making those holes bigger and bigger allows you to make a lower and lower energy platform for non-abelian anyons. Those holes are going to be connected by what I'll call a tunable bridge. This is a small segment of the Kitaev material that I assume can be tuned dynamically between one of two configurations. So first, I'm going to assume that the interior of that bridge region can be tuned to a spin liquid phase, just like the surrounding region. If the bridge realizes a spin liquid, then those two holes are just completely disconnected from one another. Essentially, they don't know about each other's existence. Now, I'll also, the second configuration I'll assume that the bridge can be tuned into is also a trivial phase. So I'm going to assume that you can nucleate magnetic ordering into that central region. In this trivial configuration, then there's another set of edge states just above and below that actually link up those two holes. So in this trivial bridge configuration, you should think about those two holes as being kind of linked into a single dumbbell-shaped hole that just hosts a single chiral Majorana edge state roaming all the way along the perimeter. All right, so suppose now that starting from this trivial bridge configuration, on some time scale, on some finite time scale, I evolve the bridge from trivial to spin liquid, okay, going from connected holes to disconnected holes. So we can get some intuition for what happens here by considering some extreme limits. So first, if that manipulation was done adiabatically, then assuming you started in the ground state, then you'll just end up in the ground state for these holes. And the ground state for those holes, once again, does not want any anyons there. And so you'll just, you won't wind up doing anything interesting. There will be no anyons anywhere in the system, and that's not good. So we don't want to be adiabatic. On the other side of the extreme, you can think about going very fast, doing this very rapidly. You can think about the limit of kind of a sudden perturbation in quantum mechanics. That's also no good because if you evolve that bridge too rapidly, then this bridge region will just be trapped in some highly excited state with a bunch of unwanted bridge excitations. And that's also no good. So we don't want to be too fast either. Now, interestingly, there's a broad window of intermediate timescales in which the bridge gets basically initialized into its local ground state. But at the same time, you pull out a pair of non-abelian anyons from the vacuum, dragging one non-abelian anyon to the left hole and another non-abelian anyon to the right hole. Okay. All right, so this is a way of dynamically creating anyons. And once those anyons are formed, although they cost energy, they're in an excited, the system is in an excited state, they're prevented from relaxing because they're just immersed in some gapped region all around the holes. All right, so a natural question is, if you want to realize this protocol, how do you do it in practice? How do you actually imagine forming these holes and manipulating the bridge on the timescales that would be required to make this kind of thing work? So to address this question, we envision taking advantage of tools that were developed in the spintronics community. In particular, we envision integrating the Kitaev material into magnetic tunnel junction arrays. So here's a side view of what we're imagining. So think about, so imagine for the moment, we just focus on this bridge region. If that bridge region is surrounded by ferromagnets above and below, the behavior of the bridge will be very sensitive to the relative orientation of those two ferromagnetic moments. Okay, so if those ferromagnetic moments were orienting anti-parallel to one another, then you can think about the bridge as basically seeing zero effective magnetic field, placing that part of the system into the magnetically ordered phase of the Kitaev material phase diagram. On the other hand, if those ferromagnetic moments align with each other, if they align along a common direction, then the Kitaev material looks like it's experiencing a non-zero Zeeman field. And we assume that that non-zero Zeeman field places the system in the spin liquid portion of the phase diagram. And so by toggling the relative orientation of these magnetic moments, you can, in real time, toggle the system between trivial and spin liquid phases, in principle giving you a pathway towards manipulating not only the bridge, but also these holes on nanometer and nanosecond scales. All right, so this I think is not simple, but I find this a very appealing in the long run, because at least for the first time, I can see a pathway towards actually having the kind of length and time scale requirements, manipulation requirements that would allow us to perform the kind of manipulations we would like to do for actually not only creation of non-abelian anyons, but as I'll describe now, also manipulation of non-abelian anyons. Okay, so I'm running a little bit low on time, so maybe I can ask for some advice about whether I should try to just kind of close, or.
Yeah, I would say that you can continue for 5-10 more minutes.
Okay.
If that's okay.
Yeah, sounds good. Okay, so let me very briefly describe how we can use the same trick of holes and bridges to not only create non-abelian anyons, but also braid and fuse them. All right, so let's consider a slightly more elaborate setup in which I have not 2, but 4 of these holes connected by 4 bridges as shown by these dashed lines. I'm going to assume for this initial setup that we've successfully applied this dynamical anyon generation protocol that I just sketched to you to create a non-abelian anyon, one in this upper left hole and another one in this upper right hole. Okay, so what I'd like to do now is describe how we can, by manipulating the holes and bridges, we can perform a braid of these 2 non-abelian anyons, and then I'll show you how you can fuse as well. All right, so first thing I'll describe is how we can transport this non-abelian anyon down into the lower right hole. All right, so the first step, I'd like to take this, the hole perimeter, and shrink it. Okay. Now, when I shrink that hole, I increase the energy for that non-abelian anyon, because remember the energy cost for having a non-abelian anyon scales like 1 over the perimeter. So by shrinking the perimeter now, this costs more energy. And so this non-abelian anyon, if given the chance, would like to escape to a bigger hole where it can lower its energy. We can indeed give that non-abelian anyon a chance to escape by just taking this bridge here and evolving it over some adiabatic time scale from spin liquid to trivial, connecting those 2 holes into a single dumbbell-like hole. And then I can just so that has the effect of basically spreading out that non-abelian anyon along this entire dumbbell. And then when I move back to the spin liquid bridge configuration, this anyon can just stay where it would like to be in this bigger hole, okay, where it costs less energy. So essentially, there's like a force that's drag that anyon downwards. Okay, and once I've transported that anyon downwards, I can reinflate that upper right hole and go to the configuration I started with, but now with the with this non-abelian anyon displaced. So similarly, you can perform the same kind of manipulations for these bottom holes to transport the non-abelian anyon leftwards. Then you can similarly evolve the upper two holes to move this non-abelian anyon rightwards. And finally, you can move this non-abelian anyon upwards. So that's just to find a single swap of those non-abelian anyons. So braiding is actually even more straightforward. Fusion is actually more straightforward. I simply need to, if I want to fuse these two sigmas that I've just swapped, I can just evolve the bridge here from spin liquid to trivial, and then combine those two holes into one, which has the effect of fusing those two non-abelian anyons. All right, so that's a strategy for not only creating, but also manipulating manipulating Kitaev spin liquids to implement braiding and fusion. All right, so with maybe the last few minutes I have, I will describe a backup plan. As I emphasized in the discussion of alpha ruthenium chloride, the experimental situation there remains murky. I hope things will get settled in the interesting direction. But you know, we should think about possible alternative scenarios just in case Kitaev materials don't actually give us the gift that we hope they do. So what I'd like to describe in the very last part of my talk is some alternative way of generating Kitaev type spin liquids, Kitaev honeycomb type spin liquids that potentially suggest new avenues for realizing non-abelian spin liquids and non-abelian anyons. All right, so I'm going to now focus on a very different kind of spin system. Actually, this is probably my all-time favorite physics problem, by the way. So let's just consider the transverse field Ising model. So let's consider a chain of spin and a half degrees of freedom that couple via their nearest neighbors via an Ising-like interaction that just couples the z components of neighboring spins. And we'll introduce a transverse magnetic field, which wants to polarize the spins along, let's say, the x direction. Okay, so this is once again the classic problem of transverse field Ising model. Here's a phase diagram of that Ising model as a function of h over j, where h is the transverse field and j is the coupling energy, the Ising coupling energy. So when the transverse field is very small, the J term wins, and the system will just realize a ferromagnetic state where the spins want to polarize all up or all down. But eventually, when you increase the transverse field beyond a critical value, you destroy that ferromagnet in favor of a paramagnetic state, where the spins just point along the x direction. Now, this is a classic example of a quantum phase transition. The quantum phase transition that separates these two phases is very well studied and is a quite interesting phase transition that hosts emergent fermions. Okay, so when you hear the word emergent fermions appearing again, this might ring a bell. This actually sounds reminiscent of the situation for the Kitaev honeycomb model, where we also had emergent fermions arising from a spin system. But in this context, there's a crucial difference because these emergent fermions roam around in one dimension. They were born in a spin chain, whereas in the Kitaev honeycomb context, we had emergent fermions delocalized in a two-dimensional spin system. But nevertheless, I'm going to exploit this tantalizing connection, the existence of emergent fermions, to leverage this quantum phase transition to try to design new avenues to getting two-dimensional Kitaev type spin liquids. All right, so if we park ourselves at this phase transition, then rather than thinking about spins as the relevant low energy, as the useful low energy degrees of freedom, instead we should think about having a right and left moving set of fermions that are the quote unquote right degrees of freedom to be thinking about at least at low energy scales. All right, so now imagine that I take not one of those quantum critical spin chains, but now imagine that I take an array of such transverse field Ising chains. All right, so now I have right and left moving emergent fermions, one set for each chain. So I have a lot of these now, and we can try to now design interactions between those adjacent chains to liberate the fermions from the chains in which they were born. Okay, so this is actually the non-trivial step. I'm gonna hide all the details, but there are certain kinds of interactions that we believe will spontaneously liberate these emergent fermions from the chains in which they were born, in which case one gets emergent fermions that roam not just in 1D, but in the full space of this two-dimensional spin chain system. All right, so quite amazingly, if you work out the band structure for these fermions once they delocalize, one will find a single Dirac cone, indicating that despite the very, very different starting point, we've landed in the same gapless spin liquid phase as in the Kitaev honeycomb model. All right, so the fact that we have this completely different way of accessing the physics suggests that maybe there are new kinds of systems that look nothing like the honeycomb, model, but nevertheless harbor basically the same phenomenology. And in particular, we've been thinking about Rydberg arrays, so atoms trapped in optical tweezer arrays, as particularly appealing settings in which to explore this kind of construction, basically because we think that the kind of interchain interactions that we would need to generate this kind of state can be rather naturally driven in these Rydberg array platforms. All right, so I'm quite excited about this work. I think it, again, opens up a new lens into the physics of Kitaev spin liquids and gives us, I think, an appealing backup plan in which we can envision applying some of the ideas that I described earlier for detection and generation and manipulation of non-abelian anyons. All right, so let me now end. Basic takeaway messages are that Kitaev materials and I hope Rydberg arrays offer promising platforms for non-abelian anyons and perhaps down the road topological quantum computing. The roadmap is in development, but we've made quite a bit of progress in the last couple of years thinking about how we can profitably exploit these electrically insulating compounds for anyon creation, anyon manipulation, and single-anyon detection. These are the basic ingredients we need to try to work our way up towards quantum information applications. Fortunately, experimentalists are taking notice. There's at least a growing body of experimentalists that are interested in pursuing some of these directions. And so it'll be interesting to see how far we can push this agenda. So thank you very much for your attention, and I apologize for going a little bit over time.
Thanks a lot, Jason, for the wonderful talk and for telling us about these extremely inspiring strategies for creating and manipulating anyons in quantum spin liquids. So now we have some time for questions, and if you have any questions, you can either raise your hand or you can write it in the chat. And I don't see any questions so far, so I can perhaps start with the first one. So for this strategy for creating anyons, you have to make some holes in the quantum spin liquid. So in the case of ruthenium trichlorine, what would be the length scale of these holes that one would need to create?
Very, very good question. Okay, so let me, sorry, go back here. All right, so, okay, so first let me say what the requirements depend on. So I think what would ideally set the size, the ideal size for these holes is the optimal time scale over which you would want to manipulate that bridge. So I mentioned, let me scroll through a little bit. So I mentioned that we want to be neither adiabatic nor too fast. And so you can ask, what defines being neither adiabatic nor too fast? And so there's some characteristic timescales which depend on the geometry, the size of these holes and the size of those bridge that quantify the window of timescales. That's kind of the sweet spot for carrying out this algorithm. And so, first of all, there's geometric factors that are involved, and there's also energy and velocity scales, in particular the size of the gap for the spin liquid is another relevant scale, and also the velocity for those edge states. Now, so if you, let's say, assume a 5 Kelvin gap and reasonable velocity like 10 to the 3 meters per second for the edge state, then if these bridges and holes have kind of tens to hundreds of nanometer scale geometries, then the corresponding time scale that you would need to perform these manipulations on is in the nanosecond realm. And so that's kind of the realm where it starts to get experimentally plausible. If you want to go much faster than that, that begins to be very experimentally challenging, although not impossible. And so I think the upshot is that depending on scales, I would say we're looking at scales on the tens of nanometers to submicron length scale. but the precise scales really they're material dependent, and they depend on factors that we don't quite know with precision yet.
Great, thanks a lot. So now there's another question in the chat, which is, hi, thanks a lot for the talk. I would like to understand better how does shrinking the trivial region would help with braiding?
Okay, yeah, so okay, so suppose that let me advance a little bit. Suppose I didn't shrink this hole. So then when I connected these two holes together and then disconnected them, there would be no preference for the non-abelian enyon to have moved downwards. Okay, so by shrinking one hole, I basically it's sort of like I provided a force because the non-abelian enyon costs less energy when it lives here, right? So by shrinking one of the holes, I kind of provide a potential landscape for the non-abelian enyon. It's sort of like a slide, so it would like to slide down if given the chance to go from this higher energy region to this lower energy region. And this is maybe not obvious. This depends on some features of the edge theory that's describing the boundary of these holes. But once again, you know, the energy cost for this non-abelian enyon it scales inversely with the size of that hole. So the smaller the hole, the bigger the energy cost. Does that help?
Yes, it helps. Yep.
Well, maybe I can ask one more question. So, I mean, this is maybe very pedestrian, but so you have different kinds of quantum spin liquids. And okay, so this only applies for you need to have a gap topological quantum spin liquids so that you can develop these schemes or how is it? So
yeah, no, that's a very good question, because there's a zoo of different kinds of quantum spin liquid phases that can arise. Some are gapless, some are gapped. There's different kinds of gapped spin liquids. So the really key ingredients here, okay, so there's certain features of what I've described that don't require non-abelian spin liquids, and that could apply even to certain kinds of gapped spin liquids that didn't have non-abelian anyons. The really crucial thing for pretty much all of the manipulation and readout strategies that I proposed is having this chiral edge state. I was exploiting that chiral edge state heavily pretty much for everything I did, for the single-anyon detection strategies, because the energy was funneled along a predefined route. The enyon generation protocol exploited the fact that I had an edge state that kind of was a cheap place for enyons to exist. So all the strategies that I laid out can be equally well applied to any gapped spin liquid that has a chiral edge state. The non-abelian enyons is kind of a bonus. But I think there are plenty of gap spin liquids that don't have chiral edge states. For instance, the toric code, which some of you may have heard of, that's a classic example of a spin liquid that doesn't have a gapless edge, and that's a more subtle situation, I think, to try to envision how to manipulate and at least in solid state manipulate and detect emergent degrees of freedom in that context. So nothing I described here, I think, would carry over to that context.
Yeah, thanks.
Sure.
All right, so I think that there are no further questions, so I would suggest that we can stop the official part of the colloquium now. So first of all, thanks a lot, Jason, for this wonderful and inspiring talk on enyons in quantum spin liquids. Thank you, everybody, for coming.